Okay, last time we looked at the experiments of James Joule, and Joule showed that he could convert, motion into heat, and a certain amount of motion always led to a certain amount of heat. And that made much more convincing this idea that heat was actually a form of motion, some internal motion of the atoms that make up a body. Since there is this constant relationship between motion and the amount of heat that it can generate. So, it made plausible the idea that what you're doing there is just converting this external motion into some internal motion of the parts of the body. But that still leaves it pretty vague in terms of what, to say that that heat is a form of internal motion leaves open the question, what kind of internal motion? Exactly what is heat? What mathematical function of motion is it? There's lots of. How does it depend on the velocity of these atoms, for example? Joule didn't answer that question. Okay, now it turns out that right around this time that Joule was doing his experiments, another guy did answer that question. And the problem that he was thinking about was gases. And he came up with a simple atomic model of gases that turned out to give an incredibly important result that made clear exactly how heat is related to motion. So that's what I want to tell you about this morning. Now, before I do, let me give you a little background, and this will just be a review of stuff that we've talked about before. So you can call this in your notes background. Okay, so I just want to, there are certain things we've already covered about gases that are going to be crucial here. And the main thing here is something that's called Charles' law. Now, don't everybody shout it out at once. What's Charles' law? Anybody know? It's the basic law of gases, relating things like pressure and volume and temperature. Troy, take a shot at it.
Is it that pressure times volume equals the number of moles times a constant times the temperature?
Yeah, that's. I think that's even better than what I told you in class. Where did you? Oh, your math book has that. Okay. Yeah, that's really good. I'm going to write it in a slightly different way. You actually, the way you stated the law is absolutely correct, but it actually goes beyond what Charles knew. So first, let's start with what Charles knew. The pressure times the volume of the gas is proportional to, well, what Charles actually found was the temperature in Celsius, okay, the Celsius scale, where room temperature is about 20 degrees. So, okay, plus 273. Hmm? Yes. Okay, but that's how the conversion to Kelvin was discovered. That Charles just found experimentally that the pressure times the volume was proportional to, what they were calling the temperature at the time, the temperature on the Celsius scale, plus this number 273. And so then it becomes natural to define a new temperature scale, which later became known as the Kelvin scale. So we'll just call this, Kelvin temperature, T sub K. Okay, now for, there were other things. The reason I'm not writing equal signs here is because there is some proportionality constant here. Now, one thing that you know about that proportionality constant is that it has to do with the amount of gas that you have. For example, let's say you have a certain amount of gas, say oxygen. Now, if you keep the temperature constant and you keep the volume, say, constant, and but you shoot twice as much gas into your container, okay, so you double the amount of gas, what's going to happen to the pressure? Yeah. Huh? Yeah, it's going to double. Right. So this proportionality constant here, it has something to do with the amount of gas. And for a given kind of gas, if you double the amount, you'll double the pressure. Now, the confusing thing for scientists at this time was that the proportionality constant did depend on the type of gas. For instance, if you're just working with oxygen gas, okay, if you double the mass of your oxygen gas, okay, you'll double the pressure. But if you, let's say you have hydrogen gas. Well, if you double the amount of the mass of your hydrogen gas, you'll double the pressure. But it turns out that you can have a much less mass of hydrogen gas compared to the oxygen gas and still get the same pressure. Okay, so it did depend on the type of gas and the mass of the gas, so the total mass of the gas. So that's what scientists knew at this time, back in Charles' day. This was, I could ask you the year, but I don't know whether, you probably don't remember this one. This was 1785. Okay, so this is, you can understand this much about gases without thinking about atoms at all, right? Just doing experiments relating the pressure, the volume, and the temperature. All right, now, a guy comes along, J.J. Waterston, in the 1840s, and he decides to think about these properties of gases in connection with the atomic theory and see how far he can get in understanding the behavior of gases in terms of a simple atomic model. So let's look at what he did. Okay, so this is J.J. Waterston. And he did this in 1845, I believe. Right after, in fact, he had just heard about Joule's experiment when he did this analysis. Okay, now he decided to model what was going on in a gas in a very simple way. First, it was known that, he believed in that matter was composed of atoms. So he's going to try to analyze gases in terms of atoms. Now, if you think about what's going on in a gas, well, certain things are clear just from experiment. For instance, if you take water and you boil it off into steam, well, the steam takes up an enormous volume compared to the original water. It turns out it takes up like 1,500 times, as much space as the original water. So what does that imply if you think in terms of atoms? Troy?
The atoms are pretty spread out.
Yeah, the atoms are pretty spread out. There's a lot of space between the atoms. So Waterston starts thinking about this, and he thinks, well, maybe I can pretty much ignore any interactions between the atoms, as a first cut at understanding this. Because they're pretty far away from each other. They're spread out, and maybe I can just treat them. Well, he has the idea. He's going to treat them like little superballs. Okay, think of it this way. Let's say that we've got a bunch of oxygen and nitrogen molecules in this room right now, right? J.J. Waterston's idea is that you can treat each one of these atoms like a little ball, and it's just careening around the room. It's traveling at, it just travels at a constant speed until it runs into something. Then it bounces off, with that same speed. So it doesn't lose speed when it bumps into a wall, say. Now, the same thing is true. That's what I meant when I said that he's treating them like little superballs. Because if you take a superball and you throw it against the wall, okay, it doesn't lose any of its velocity when it hits the wall. It just bounces right off with the same velocity. And so Waterston's idea is we've got basically a room full of superballs here, careening around off the walls and the floor and the ceiling in all directions. That's what a gas is. Now, obviously, if we actually had that in this room, and we started bouncing these superballs around, and we came back an hour later, superballs would just be laying on the floor, right? They'd eventually slow down and stop bouncing around. But Waterston figures, well, that's just due to air resistance and the fact that they're not perfect superballs, so they lose a little bit of their velocity when they bounce off the walls. But he says, well, let's say atoms are perfect superballs. And of course, there's no air resistance. They are the air. So the So he's going to assume they never lose, their velocity. They just keep bouncing around. Okay, so simple atomic model. Let's call it the perfect superball model. Now, let's just to make. Now I'm actually going to take you through a little bit of math here that Waterston had to do in order to reach his result. Now, before we start into the math, we're going to make things really simple. I mean, considering millions of superballs all bouncing around in different directions, if we tried to just jump right in and analyze that, which is really Waterston's view of what a gas is, that would be complicated to keep track of all million of them and going in all different directions. So it turns out you don't have to do that. Waterston was clever at simplifying the problem. He just starts out and he considers the effect of one superball. And at the end, he's just going to multiply by the number of superballs. Okay? Simple. We ought to be able to analyze one superball, right? Okay, so furthermore, he's going to start out, he's just going to assume that his room is a cube. Nice, simple geometric arrangement. Okay, so here's our situation then. We have a cube. We have a superball that, say, is bouncing back and forth between these two walls. Okay, everybody get that simple picture? Superball, I'm going to pick a direction. My superball is bouncing back and forth in this constant direction. So all this superball is doing is just bouncing back and forth between these two opposite walls. Now, let's calculate, say, the pressure on this wall. Now, what is pressure? Well, pressure is force per unit area. That's the units of pressure. Okay, so it's the the force on the wall divided by the total area of the wall. Okay, now let's say this cube has sides of length L. So pressure is force per area, and if I express that in terms of L, what's the area? Daniel.
L squared times 6.
Oh, the total area of the cube. That's the surface area of the cube. That's right. But if we're just calculating the pressure on this wall, this one face, it's just L squared, right? Okay, now what do we do with this force term, though? How do we figure out the force that this super ball is imparting on that wall? Evan, any idea?
Well, the mass of the Super Bowl.
Yeah.
That's how fast it's going.
Well, almost. Now, what was Newton's fundamental law of motion? It was force equals mass times, not velocity, but acceleration. Exactly. And what is acceleration? Acceleration, try. Change in velocity per time. Right? It's the rate of change of the velocity, okay, with time. So let's now write that expression for the force. Here we have the mass of this little super ball, and call the change in its velocity when it hits the wall as delta V. And the time interval between hits as delta t. So let me actually write those down. So delta V is equal to change in velocity on impact. Delta t is the time between impacts. In other words, if this thing is hitting once a second, okay, we want the change in velocity that it undergoes when it hits, over that 1 second interval. That'll give us the rate of change of velocity. Yes?
But won't delta t just be constant the whole time?
Yeah, delta t is just going to be a constant for a given speed of the ball. Right? Exactly. But we can actually work out what these things are now. What is the change in velocity on impact? Well, okay, I know what you're about to say. You're about to say that there isn't any change in velocity because I already told you that the speed stays the same. But what happens? I mean, obviously something happens when it hits that wall. Nick?
Velocity changes direction?
Yeah, velocity completely reverses direction. So, one instant before it hits the wall, you've got it going this way with a certain magnitude, okay? The next instant, after it hits the wall, you've got it going completely the other way with the same magnitude. So what's the total change? I mean, this is a bigger change than if the ball just impacted and stopped, right? Because it's completely reversed. Nick?
Changes twice the
Twice the speed, right? because it lost all its initial speed going in one direction and gained that speed going in the exact opposite direction. So the total change in velocity is 2 times the magnitude of the speed. Now, Nick. Oh, it's the mass of the superball. Right, because, yeah, I actually should have written, remember, so recall Newton's basic equation. Okay, so that's what I'm using here. So I'm just substituting for force the mass times the change in velocity over the change in the time. Now, let's do the time now. What's the time interval between impacts here? Oh, I said I was just making up a number. But if we express it in terms of the, I want an expression in terms of the speed and L. Nah, this is easy. Wait, here we have a proposal of L over 2V. Hmm?
L over V.
Yeah.
L over V, okay. We have a change. Now we have L over V. Well, now remember, it's time interval between impacts against this wall.
Yeah, so it is L over 2V.
It's,
Two over.
now you've got it. Why 2L over V?
Because it's not between the two walls, it's going between the walls twice.
Right, it has to go against it after it bounces off this wall. What does it have to do before it hits it again? It has to go all the way to this wall. Okay, so it's gone a distance L, and then back to this wall. So it's on a total distance of 2L. Okay, at this speed. Okay, so if you had to go a distance of 2L, at speed v, requires you just put the distance over the speed to get the time. So 2L over v for the time interval. Okay, now let's put all this together. We've got all the pieces now. So let's let me erase some things. So we have the pressure. All right, I'm going to try switching colors here. Here we go. The pressure equals, let's just start by repeating this, the equation I've already written down. And now we substitute. For delta V, we substitute the 2V. And for delta, well, let me do it this way. If delta t is 2L over V, 1 over delta t is V over 2L, right? So V over 2L.
So it's just
All right, we can keep doing the algebra here.
m equals 2v squared over.
So we have 1 over, let me write it this way, L cubed Everybody agree with that?
Yep.
Well, that's kind of an interesting equation. Troy.
Does anybody have like a term for the mass of an atom or not?
Oh, yeah, it's called the mass of an atom. Well, it depends on the atoms. We've already seen that. Remember that we've seen hydrogen is. I mean, we've already seen scientists, chemists, and physicists figure out that hydrogen is the lightest of the atoms, and oxygen atom weighs 16 times as much. Remember, so they figured out these relative atomic weights. So yeah, keep that in mind. We're going to get to that in a minute. But I'm not quite done here. This L cubed that popped up in the equation is kind of interesting. What would, yeah, it's just the volume of the cube, right? So now, this is looking too busy right now, so let me get rid of the stuff that all of you already understand. Okay, now, so how could I rewrite this? Pressure times, let me see, big V, just so I'm going to put little, I'm going to write big V like this just to make sure that you don't confuse it with velocity. Equals the mass of our superball or atom times its velocity squared. Well, that's pretty nice. Nice, simple result. Now let's go ahead and compensate for the fact that we've only been thinking about one superball here. I mean, we might as well take account of all of them now, right? And there's millions and millions and trillions and billions of them. But it's pretty easy to take care of the rest of them now that you've done the analysis for one, because all you have to do is say, well, I mean, how many directions are there here that the superball can go? There's 3 directions, right? I mean, it can go, sideways across the board, as I've drawn this thing. It can go up and down, or it can go in and out of the board. I mean, it can hit. So, yeah, it can have combinations of those directions, right? But there's only 3 directions. Okay, so so basically, I mean, you might think that to take into account that there's, say, some large number of atoms. Let's say n. N is number of, I'm just going to start calling them atoms instead of superballs now. Big N, let's call the number of atoms. Now you might think, okay, well, how do we take into account the fact that this is the result for one atom? And if we actually have n atoms, you might think that you would just do this. just multiply the result by n. But turns out that's not quite right. Now, can you think of why? Remember, this is the pressure on, say, this face, Nick.
Because they're not all going to that?
Right, they're not all going in this direction. I mean, the atoms that are bouncing up and down, say, never touch this face. The atoms that are bouncing off the other two walls never touch this face. Nick.
Or should it be n over 3?
N over 3, exactly. Okay, because on average, only a third of the atoms are going in the direction to bounce off a given wall. Okay, so all we had to do was divide by 3 in order to get the result for all these millions of atoms after we analyzed the effect of the one atom. So this is the equation I was going for. Okay, now let's think about this equation and see if it makes sense. Well, okay, so you've all got this in your notes now. Let me actually transfer that. Up here. And so I can clear some space on the board. Now, well, it turns out that this quantity here of the mass times the velocity squared was not new to physicists. Let me just let's just call this, well, let me say something else first. Okay, so now we've got this result. And now the question is, does this result make sense? In other words, we can't do any direct experiment to check this, right? Because we can't see the atoms, we can't measure their velocities. So how are scientists going to decide whether this is just some product of Waterston's imagination or whether this actually captures what's going on in a gas? See, it's a tricky problem that they face now. I mean, it's, is this fantasy or is this science? And the way they're going to decide that is by, the way they should decide it is by seeing how this fits in with everything else they know. I mean, if this explains a whole bunch of things that they already know are true, then they've got to believe this. On the other hand, if it doesn't really connect to or explain anything else they know, then Waterston hasn't really accomplished much. Okay? Now, in fact, actually, I might as well tell you this now. Waterston was one of the most abused physicists in history. He did this brilliant analysis, and he submitted a paper to the leading scientific journal of the day, the Transactions of the Royal Society. Okay, and it wasn't just rejected; it was rejected emphatically. The reviewer said, "Let me see." Quote, "The paper is nothing but nonsense, unfit even for reading before the society." Okay. Now, so Waterston's work was completely rejected. And the idea of these reviewers that saw the paper and didn't think anything of it was, I mean, they judged this to be fantasy. Okay. They figured, well, I mean, yeah, Waterston can make up this silly model that that gases are collections of billions of superballs bouncing around, and you can derive this equation from that fantasy, but it doesn't connect with observation. Okay, we can't see any of these atoms. So that was their objection basically to Waterston's paper. But it turns out Waterston was right, and the reviewers were wrong. And the reviewers should have asked themselves a whole bunch of questions about the implications of this equation and what it meant in terms of, I mean, did it make sense from the point of view of Newton's basic laws of motion? Does it make sense and explain anything that the chemists have discovered? And the answer to all those questions was yes, turns out. It is a tremendous explanatory power in this equation. And that's why they should have accepted the paper. They weren't smart enough to. Troy?
Was it later accepted by some other people?
Well, what happened, actually, was this result was rediscovered 12 years later by a German physicist. And by that time, there had been some other developments in physics, and the people ended up accepting it. And then, about 50 years later, somebody was reviewing the old notes of the Royal Society and came across this paper by Waterston, and then exposed, what had actually happened. That in fact, Waterston had been the one to derive this very important result and had never gotten the credit for it. Yeah. Yeah, Waterston was dead by then. It turns out this wasn't even the only time this happened to him. He derived other important results on the speed of sound, for instance, and those were rejected. So he did not have the career that he should have had, and he never got the respect he deserved. But okay, so what we're going to do this afternoon, though, is see why this result should have been accepted by looking at all the things it explains that scientists already knew about. Okay, but that's all I got time for this morning.